Bom dia a todos e a todas. Então, vamos dar início a mais um colóquio do IFSC. O colóquio, só para o pessoal que está acompanhando no YouTube, se vocês tiverem perguntas e dúvidas, podem colocar no chat do YouTube, a gente passa para o palestrante. Eu vou mudar para inglês, because today we have the pleasure of receiving Professor Rajesh Narayanan. And for the introduction of Professor Narayanan, I'll invite Professor Abel to introduce him. He's a guest here in our institute this week, for this month, I think.
Yeah, for a little bit more than a month. And to introduce Raj, I will switch back to Portuguese because I don't want to embarrass him with so many compliments. Bom dia a todos, bem-vindo a mais um colóquio. É um prazer para mim introduzir ou apresentar o palestrante de hoje, o professor Rajesh Narayanan, do Instituto de Tecnologia da Índia, na cidade de Madras. Raj eu já o conheço nem sei desde quando eu o conheço, mas ele tem sempre trabalhado no tema de sistemas desordenados ou efeitos de desordem em sistemas de matéria condensada, que é onde eu trabalho também, então é natural que a gente tenha se encontrado. E desde o meu primeiro encontro com ele, é a pessoa mais carismática e gentil que, talvez não a mais, mas certamente o indiano mais carismático e gentil que eu conheço. É extremamente prazeroso conversar com ele sempre muito sorridente, sempre muito positivo, muito para frente, sempre pensando em novos problemas. A gente dá um problema para ele, fala uma solução, ele já vem com outra pergunta, então está sempre muito ativo, sempre levando o campo para frente. Então, é muito legal colaborar com o Raj. Um pouquinho do currículo dele, ele fez a sua graduação em Física na Universidade de Bombay, em 91, depois fez o mestrado também em Bombay. Em 99 foi para os Estados Unidos, na Universidade de Oregon, onde obteve seu doutorado em 99. Depois passou 2 anos em Oxford como postdoc, mais 2 anos no Instituto Max Planck, na Alemanha, em Dresden, mais 2 anos. E depois mais uns 2 anos no Instituto Tecnológico de Karlsruhe, também na Alemanha. E em 2006 ele voltou para casa, voltou para a Índia, onde eles estão, no Instituto Indiano de Tecnologia, na cidade de Chennai. E já há um tempo é professor titular nesse instituto. Tem publicado bastante e orientado muitos alunos de mestrado e doutorado. Bom, com isso, eu vou passar a bola para o Raj. Raj, now I switch back to English, and it's now up to you. Thanks for coming. And
I don't have to go there? Okay. But as long as I don't fall down, it's fine. So it's nice to be here. So before I start, I would like to thank Professor Jose Hoyos, who has been a wonderful host. It's great being in Brazil. The people are extremely friendly. The food is amazing. And this coming from a country like India, which has a very amazing food culture, you guys have an amazing food culture, and I love it. And I love staying in Brazil, so this is my second trip here. And I would like to thank IFSC for hosting me. It's been an absolute pleasure working with Jose. And what I'm going to talk to you is actually related to some of the work that I have been doing with him, or related to some of the work that I have done with him for the past some time. Okay, so first of all, I have to tell you that this talk is not for the experts in the audience, and there are a lot of experts in the audience. Jose is there, Professor Alcaraz is there, and many other experts in the audience. This is not for you, this is for the students. Okay, so I also know that you have to go to your canteen by around 12, otherwise it gets too crowded. So I'll try to be fast. I'll try to convey whatever I have to convey before that time. So the title of my talk is Quenched Disorder, Friend of Foe in Condensed Matter Systems. Quenched disorder, I'll come to in a minute. Whether it's a friend or foe is something that we will see towards the end of the talk. So the simplest sort of phase transitions that we have seen in our daily life is, of course, the liquid-gas transition or the solid-to-liquid transition. For example, you start melting ice, right? What happens when you melt ice? You start heating it. The temperature of the ice essentially starts going up. But at some point, you essentially start melting the ice into water. So at that point where you start melting the ice into water, there is a coexistence of the two phases, the liquid and the gas. Sorry, the solid and the liquid, correct? So there is a coexistence of phase. You keep supplying the energy, that energy, the heat. The heat is used to melt the ice. And essentially what happens is you have to wait until all the ice is melted before the temperature can start moving up again, right? So in fact, such systems where there is a coexistence of the two phases and where there is what is called as latent heat that has to be supplied to melt this object is what is usually referred to as discontinuous transitions, right? So many of these phase boundaries here correspond to such discontinuous transitions, except for that little red dot over there. So what happens is as you start, what is it called, go into the liquid phase and then you start heating it, as you go to larger and larger temperatures and pressures, what happens is there's no distinction effectively between the liquid and the gas, and effectively you hit what is called this critical point, and then at this critical point there's no coexistence anymore, there's no latent heat anymore, and some very interesting things happen at this critical point. In a similar manner, you have the magnetic transition where you have coexistence of the, say for example, the down spins and the up spins essentially, correct? And then as you tune to this critical point, which is like the Curie point, you essentially find some very interesting physics. Now what do you mean by you find very interesting physics? What it means is if I measure certain thermodynamic observables. So for example, if I measure things like the magnetization, or if I measure things like the specific heat or the susceptibility, then each of these things show very interesting power law behavior, correct? And it's this power law behavior that I'm actually going to be after. So of course, the question that anyone should ask is, why are you interested? So there's this entire phase diagram. Why are you interested in this single point, just one point in the entire phase diagram, right? I mean, that seems to be a horrible waste of resources, correct? So there is a reason why one essentially studies this one single point, and that the reason is as follows. As I told you, if I look at, say, the magnetization, right, or for example, the difference between the liquid and the vapor densities, right, these things essentially vanish as you come close to what is called the critical point, which is denoted by this Tc. In this case, I have taken the magnetization as a prototypical example, and the magnetization actually dies out as a power law, okay? Similarly, if I look at the susceptibility, and what is the susceptibility? It is essentially the reaction to an externally applied, it's a reaction to an externally applied field, and so it tells you how the magnet reacts to an externally applied field. So this susceptibility is known to diverge as you approach this critical point, and it diverges as a power law, correct? Similarly, if you were to essentially image the system, right? What you do is you take some scattering experiment, you image the system. What you do is you measure something called a correlation function. So in the language of magnets, what it tells you is that it tells you something about spins sitting here and how well they are correlated a large distance away. So away from the critical point, this correlation function g of r essentially dies out as this exponential, and the way it dies out is controlled by this correlation length psi. So what is this psi? The psi is that as soon as you're coming close to the critical point, what happens is larger and larger regions of the system are essentially getting correlated. That means if you flip the spin in one of these regions somewhere here, the spin sitting within the region, within that region essentially feels its effects. So how big are these regions? And that of course depends upon how close you are to the critical point. So essentially what happens is as you're coming closer and closer to the critical point, this length scale actually keeps becoming larger and larger. And how does it get larger and larger? Again, it's a power law, right? Of course, there is always a question of, all right, it's all power laws. Why are you so interested in this? Okay, so I'll come to that thing in a minute. The last thing that I would like to do is to tell you about what is called as critical slowing down. And what is critical slowing down? So essentially I told you that there are these large islands which are correlated. Now imagine doing a Gedanken experiment, which is the German way of saying a thought experiment, where you come in and you kick one of these islands. The islands essentially has to come back into equilibrium. To do so, for these large islands will take longer and longer time. Okay? And that is encoded in this object, which is called the critical slowing down, once again a power law. This is not going to be the case always, and we'll come exactly in this talk to situations where that's not true. Okay? So this is going to be towards the end of the talk. That's what's going to be something which is very, very important. Now, as I said, why are you interested in all these power laws? What's so amazing about these things? What is so amazing about these things, and which essentially took a lot of time for people to understand, is the concept of universality. What is this concept of universality? The concept of universality is that different phase transitions that essentially can be understood by starting from different microscopic models, okay? They have the same critical behavior. What do I mean by that? What do I mean by they have the same critical behavior? What I mean is within experimental accuracy, these exponents, alpha, beta, gamma, these exponents are all going to be the same, even though the transitions are extremely different. Now that's interesting, right? And it's very interesting for a physicist because completely different phase transitions, describing very, very different ways or very different phases and phase transitions, they have the same behavior. The exponents are exactly the same, even though microscopically they are very, very different. The question befuddled many of the big scientists in our field for a very, very long time, and it took until maybe the 70s before we have an understanding of why it is so. So the question is, how do we understand these phase transitions? So as physicists, we always have model systems. Okay, the simple sort of model. Is there a question? Yeah. So we try to build simple model systems, and from these model systems, we actually try to understand what is the underlying physics. So the simple model system is, to understand these things, is what is called as the Ising model. So this is a simple model. It is what I call the Drosophila model. Do you know what Drosophila is? Does anyone know what Drosophila is? It's a fruit fly. It is the fruit fly, and usually this neurobiologists, they actually use it as a what is it called, as a model to understand the nervous system, right? So we are trying to understand the nervous system of this phase transitions. So it's a very simple model. It has spins sitting on a lattice, and the spins are interacting only with its nearest neighbors. Okay, they talk only to their nearest neighbors. That is what this angular brackets here mean. This J is some sort of an exchange coupling, and this J is held positive. You can do negative J later on, but when we will see some very nice wrinkles that happen when you have negative J's present. And this J is positive, so it's ferromagnetic, so the system would like to align. So the system would like to be in a state where the spins are aligned with its nearest neighbors, right? That's the sort of thing that it would like to do. So what happens? So the question is, can a simple model like this help us understand phase transitions, and if so, how do we do it? So this is a model that can be exactly solved, by the way, in 2 dimensions. Okay, at 2 dimensions and lower, this model can be exactly solved, and I think some of the advanced StatMech courses here probably cover those things. But I'm not going to talk about the exact solution of this model at all. What I'm going to talk to you about today is some sort of a philosophy by which I will be able to understand the phase transitions that is presented in such sort of systems. Okay? So there's the first attempt. The first attempt is, let us think of trying to come up with an observable that distinguishes the different phases. That observable is called that order parameter. In the case of magnetic transition, it's a magnetization, right? In the ferromagnetic phase, the magnetization is non-zero. In the paramagnetic phase, the magnetization is 0. Furthermore, this is the genius of Landau. He said, let's assume that we are close to the critical point. Now, let me recollect for you that as you come close to the critical point, the magnetization is small. So he said, let's write down something like the free energy, which is effectively a series expansion in this magnetization. Okay? So you can do a series expansion in this magnetization and effectively use symmetry arguments to rule out the fact that, what is it called, the m cube, the m phi, and the odd order terms are 0. Okay? So, and what is the symmetry argument? If I look at this, this Hamiltonian S, if I take all the spins S and put it to minus S, then the system should remain invariant. That means that the effective theory, which is over here, right, which describes the same sort of phase transition, should also have the same properties. That means that m to minus m is not, it should be a good symmetry. That means no odd term should be present in the system. Okay? Furthermore, what Landau said is that the parameters, these things like R and so on and so forth, can be essentially recast into objects that look at how far you are away from the critical point. For instance, this R encodes the distance you are away from the critical point. So then Landau said, let's truncate this series at M4. This assumes, by the way, that this object U, right, which is something that comes out from the microscopics, and I'll discuss this a bit more later, which comes out from the microscopic, is an object which is positive. But let's assume it is so. Okay? Let's assume you can do calculations where this U is negative, and then you have to do some other manipulations to make sense of the theory. We will not go into that right now. So now you have a free energy which is of this form, and let's look at what happens when you are above T greater than Tc. So when you are about T greater than Tc, it's very obvious that you can that is encoded by this thing which is R greater than 0, right? You essentially see that the magnetization has one minimum, and that's at m equal to 0. What happens when T is less than Tc? When T is less than Tc, this R is negative, and obviously when m is small, it's controlled by this R, so you get this sort of behavior, and then the M4 kicks in, and then you fly up this way. Note that at this point, you essentially have a system which has a double degenerate minima, and that's exactly what you would expect from your microscopic model, because in the microscopic model, all spins aligned in the up direction and all spins aligned in the down direction should be equivalent. Okay? As long as there's no magnetic field present over here, all spins up and all spins down are exactly equivalent and degenerate. So this is the double degeneracy that is happening here. So what you can do is you can sit down, and as you can see from here, this is something like a saddle point, right? You can do a saddle point analysis of this, and out of the saddle point comes the fact that the magnetization, for instance, goes like a power law, and that power law has an exponent equal to half. You can go ahead and look at susceptibilities, and you can show that the susceptibility, which is essentially dou f by dou m, is essentially it diverges like t to the power minus 1. Okay? So the exponents, for example, half, minus 1 are those exponents that control how various thermodynamics observables behave. But there's a problem for this. I don't know how many of you have done this sort of calculations, but if you do these calculations, the first thing that you notice that something goes wrong is when you do the calculation for the specific heat. For the specific heat, you see, if you do this calculation, there's no divergence, whereas actual experiments show a divergence in the specific heat. In the case of this sort of theory, which is called the mean field theory, where you have neglected all fluctuations of the order parameter m. As you can see over here, there's no spatial dependence on the order parameter m at all. If in this case, what you can show is that specific heat actually has a discontinuity and not a divergence. So there's something going wrong there. There's another thing that goes wrong over here, and that is a simple fact that if I take this model and I put it in 1D, in one dimension, right, on a line, then you can show very clearly that there is no phase transition. You can actually do the calculation exactly, and many of you might do this very soon, right? You can do the calculations very exactly, and you can show that there is no ordered state at any finite temperature for the one-dimensionalizing model. So this is a good start. This is a good start, but it's not nearly enough, right? So I don't know how many of you have seen this American comedy series called Seinfeld. Okay, and in Seinfeld it says no soup for you, right? So no soup for you there. Okay, so and now what happens is you can show in fact that this theory does not work, at least for these set of models, for dimensions less than 4. So that means there is some dimension DC above which it holds. So this DC is what is called as the upper critical dimension. Okay, so above the upper critical dimension, it doesn't work. So this is actually a sign that one should do better. So what should we do better? So obviously the thing to do is to add in fluctuations. So now instead of the Landau theory, you have what is called as a Landau-Ginzburg-Wilson theory. Okay, the Landau-Ginzburg-Wilson theory adds in these fluctuations. It essentially adds in this grad m square term, right? And this grad m square term essentially penalizes the cost of having domains, for instance. Okay, it penalizes these domain walls. Now the question that any student should have asked is, why only grad m square and why not higher order gradients in M? There are these higher order gradients in M, but there is a systematic way of actually eliminating them, which we are not going to go into. Okay, so now we have written this very interesting theory, and this theory can be derived from purely symmetric grounds and by going through the Landau-Ginzburg-Wilson arguments, or it can be actually derived from microscopic models. Okay, so starting from the microscopic model, there is a well-established procedure to derive this, and I'll say a few more words about this when we come later in the talk. But given a theory like this, and suppose it actually tells you something about the phase transition, what do you have to do to incorporate the effects of fluctuations and so on and so forth? So this was a thing which was essentially a huge problem until the 70s, right? Okay, for you guys, 70s may seem so far in the background, but for us, it's okay. It still was modern, right? So right up into the 70s, we were jostling with how to study the phase transition in these materials, how given a Landau-Ginzburg-Wilson functional of this form, how do you go about doing actual calculations? The breakthrough came by Ken Wilson, who incorporated the ideas of Kadanoff and others, and essentially developed what is called as a renormalization group. So what is this renormalization group? That's a very simple, the idea is very, very simple. The simple idea is that you see that there is this correlation length, and this correlation length becomes larger and larger as you come closer to the critical point. So what it kind of tells you in some sense is that what you can do is you can integrate out the short distance physics. Okay? So what do you mean by integrate out short distance physics? Think of the Ising model again. And what you do is within the Ising model, you start blocking the spins off using a certain scheme. and then based on a majority rule, you replace these set of spins by either up or down based on the majority rule, right? So what you are doing effectively here is that you are integrating out what is it called, all the physics that live in a 3A by 3A sort of square block. That is effectively, now if you think in terms of momentum modes, it's the reciprocal space, correct? That means what you're doing is you're integrating out tiny shells of high momentum modes. Now, whatever you're doing, you're just integrating shells out. So if you're just integrating shells out, this shouldn't create for you any sort of non-analytic behavior and things like that, correct? So what it does is, when you keep integrating these things out, the various objects here, t, u, and the prefactor of the grad m square term, they all start changing under this integration, okay? They all start changing, and effectively what happens is, you can think of this change of these objects as some sort of movement in a parameter space. What is this parameter space? This parameter space is made up of the various coupling constants in the theory. So for instance, this is how things change under a normalization group. In the as you apply this in normalization group procedure, and I have not explained the complete procedure, but it's effectively you are integrating out physics that live at short distance scales. And as you keep integrating this out, there's a flow of the various parameters in this space of parameters, okay? So then Wilson came up with this very beautiful intuitive argument that says that, look, what you should look for is, think of this as what is it called, some sort of system of coupled differential equations, okay? And if you look at this system of coupled partial differential equations, what you look for is for fixed points. I mean, this must be what you have learned in your dynamical system courses. And in that space of fixed points, that is what I mean by a fixed point. That is, you apply the renormalization group, and it doesn't flow from there, okay? So you look for fixed points, and in this space of fixed point, you linearize around the fixed point and see how various coupling constants grow. So how does t grow or diminish, how does u grow or diminish, and how does other objects grow. So what you're doing, so what is it that you're doing physically? What you're doing physically is you're starting out from a Hamiltonian, and you're mapping this Hamiltonian to another set of Hamiltonians, okay? So there's a gradual map, a continuous map from one Hamiltonian to the other with various coupling constants. And all the coupling constants that can be generated will be generated, but then you will figure out whether this is an important one or not. In technical terms, this is what is called as whether an operator is relevant. That means under the renormalization group, does it grow larger and larger, or is it irrelevant? That means under the renormalization group, does it go to 0, or if it's marginal, it doesn't change at all, okay? So this, Ken Wilson then told us that a critical point is a fixed point with only one relevant direction. This is for thermal transitions. For other transitions, I'll come to in a minute. So this was a very, very good way of understanding critical behavior, because he told us also how universality comes into play. And how does universality come into play? You do the renormalization group procedure. There are a lot of operators that are generated, but these operators are actually irrelevant. So all the microscopic details that actually differentiate one Hamiltonian from the other become RG irrelevant. That means that the critical Hamiltonian would be the same even though you start out with different microscopic theories. And that explains the kind of the universality thing. And so it took all the way till the 70s until Ken Wilson came up with this thing. It also explains something very, very interesting. For example, if you look at, this was done by Vidom a long time ago. It was done by phenomenological scaling. So if you look at the free energy can be written in a form which is essentially, okay, so I have to tell you something else here. So these objects in the square brackets are what are called scale dimensions, okay? So if you look at the free energy essentially can be written in terms of these scale dimensions in the following manner. What is so important, and RG tells you why this is possible. Now, what is so interesting about this is that instead of the free energy being a function of just T or the applied magnetic field B, you can rewrite this in terms of a scaled variables. What does it mean by that? What I mean by that is, here for example, so let me be clear by means of an example. This is a data collapse so this is magnetism in an itinerant electronic system. Now what it does is there are various temperatures over here and various B fields over here. This functional form essentially means is that the magnetization written in terms of the scaled variables essentially has to collapse on two of these curves, one for T greater than Tc and one for T less than Tc. Okay? That's actually the way people figure out whether you are actually having a phase transition or not. There should be a data collapse on various observables written in terms of the right units, right, or the right scaled variables, and this should actually show a data collapse. So this is an example, and we will see more data collapses later on in this talk. Okay, and this has also been explained by RG. So now the question is, okay, we did all this theoretical setup. My friends in the lab are trying to grow these magnetic crystals, for instance. How much of this is observable? Okay? In other words, what I am trying to say is that suppose I am making a material in a lab, I am alloying two different samples or two different elements together, for instance, but my stoichiometry is just off a bit. That means that while the alloying process, I don't things diffuse through, you have some impurities coming in, you have some defects being pushed in. Will I see a phase transition, and will it correspond to whatever Wilson told us it corresponds to? That's a question that I'm very interested in, right? So the question that I'm asking is whether in the presence of impurities, does these phase transitions survive? That's the first question that anyone should ask. So the answer to that question, of course, it depends on the impurity, right? So let's look at two particular cases. So this is the most standard sort of classification that I have. So think once again the simple Ising model, but now the Ising model is slightly different. So I'm incorporating the effect of disorder. So there is so I have to model it some way. So how do I model it? I model it in the following way. I say that the interaction between the spins sitting on nearest neighbors on the lattice are not all uniform. Okay, they are not all uniform. In this particular example, they take two values. Okay, I call it J1 and J2, and they are randomly assigned. So this side talks to its neighbor by J1, and this side talks to its neighbor by J2, for instance. It's completely randomly distributed. In the presence of this randomness, the question is, does a phase transition survive? And I'll explain why there is a chance it will not survive in a minute. Okay, so but let's think about it in a physical way. What do you think is the effect of having such randomness is? Now, obviously, this J essentially tells you what the critical temperature is, right? A very simple way of thinking about it is that the critical, the simple, very, what is it called, mean field way of thinking about it is that you can have an order of magnitude estimate of the critical Tc by just saying that, look, the transition happens when the interaction energy, which is in this case some number of nearest neighbors times j, so the coordination number times j, and when that is of the order of kbTc, you should have a transition, correct? Now, if j is changing randomly from point to point, what does it mean? That means that locally there is a variation of Tc, correct? The Tc varies locally from point to point, and that essentially gets reflected in the sort of treatment that we are going to do. So you remember we started talking about the Landau-Ginzburg theory, right? How does the Landau-Ginzburg theory change under this? So it's very obvious that if the distance to criticality changes randomly over the space of the sample, that means that the mass, sorry, this T naught, which is some T minus Tc, essentially picks up a random component, delta T of x. This random component, you have to figure out what the random component is, what the distribution of this disorder is, and that sets how random this is and what way this T naught minus delta T of x randomly varies through the sample. So now, and this is exactly the case that would happen if instead of having these bonds which are random, you actually punch holes into things, right? So you just remove sites from here. It's the same sort of physics that comes into play, because now the number of nearest neighbors have changed from point to point, and essentially then that effectively changes delta T of x, right? So it's again a random. So this sort of problems are what are in the field theory language called as random mass or random TC problems. Okay. So the question that everyone was asking is, what is the effect of this random TC disorder on the critical behavior? Okay, on the critical behavior. So it's actually very interesting to figure out. So let's assume that you take the large system, okay, and you subdivide it, and you subdivide it in at the length of at the size of a correlation length into boxes. So you take your macroscopic sample and you divide this into mesoscopic boxes, each of correlation length psi. Okay, so each of this has a correlation length psi, and now you ask the following question: because of the presence of these impurities, what happens is that the distance to criticality on each of these places actually varies, or TCs. Each of these boxes have their own TCs. So each of these boxes have their own TCs. That means there is a distribution, and the distribution of TCs, and this distribution of TCs has a width. Let's call that width delta T, okay, or delta TC. Now you want to estimate what delta TC is. Right? How would you estimate what delta TC is? Remember that each of these boxes contains some n, n random variables, that is n bonds within them, which are all random. So this delta TC can be estimated by something like the central limit theorem, right? So this width essentially should go as some n to the power minus half, and then you convert that number n to the correlation length, so that's why the psi to the power minus d by 2 comes. Now what happens? If this delta T is greater than T minus Tc, where this Tc is of the global sample, then what happens is some parts of the system are ordered, whereas some other parts of the system are disordered. That means you cannot get a state with uniform global order, correct? So whereas in the opposite limit, when delta T is less than T minus Tc, all parts of the system, or almost all parts of the system, are either on the ferromagnetic side of the order or on the paramagnetic side of the order, correct? That means that if I bring down the temperature, there is a possibility for the entire system to go into an ordered phase, right? A homogeneously ordered phase. This is exactly what Harris argued, and remember that T minus Tc was actually related to how your correlation length went to infinity, correct? So you remember that psi goes as T minus Tc to the power minus nu. That means that T minus Tc goes as psi to the power minus nu, minus 1 by nu. So you essentially match this delta T with this T minus Tc and put in the condition that for a homogeneous order you should have delta T less than T minus Tc. This immediately gives you that if you want the clean critical behavior to survive, then nu d should be greater than 2. Okay? It's a very simple criteria. This can be put on much firmer grounds by using these RG theories that we were talking about, and so on and so forth. And this was done. Okay? And there's a huge body of work that attests to it. So if nu d is greater than 2, then what happens? What happens is the ratio delta T by T minus Tc goes to 0. But what does that mean? What does that mean that when I say delta T by T minus Tc goes to 0? What it means is that think of it in the language of RG. You are making these blocking schemes, you are coarse graining it. So, as you are coarse graining it, your disorder is changing under this coarse graining, right. So, the disorder is flowing in this flow space. What is happening is that the system looks more and more disorder free. That is what it means by that. That means the system looks more and more like a clean system. Okay? That means that the critical behavior that the experimentalist will measure in a lab, if nu d is greater than 2, is that going to be that of the exact clean model. So, it does not matter if there is impurities in the sample. What happens when nu d is less than 2? When nu d is less than 2, as you go through this coarse graining, disorder becomes more and more relevant, becomes larger and larger. Question is, what happens in that limit? And the Harris criterion itself is very silent about it. The Harris criterion doesn't tell you anything about it, right? The Harris criterion just says that, okay, clean critical behavior doesn't hold. You need to lay recourse to some other things to figure out what happens when this thing is violated. So, let me tell you what happens. What happens is 3 things could happen. One is the system goes to a new phase transition where this equality is not violated now. The system goes through a new type of phase transition, one of which we will see later on in this talk. The third thing is that disorder just destroys the phase transition, okay, which we will not see. We will see an aspect of it somewhere later in the talk. Are there any questions till now? Okay. Now let's look at some other limit, and that other limit that I am going to talk about, is other sort of disorder that I am going to talk about, is what is called as random field disorder. So, the sort of thing that you are doing is you are alloying this material, and by mistake at random points you are essentially putting in some random magnetic impurity, right. You are putting some, so that is a sort of thing that you should think. You are making this sample, you are putting in your alloy, and in the alloy there is some random magnetic impurities present, and that I model by this sort of Hamiltonian with a term. So, this is your usual icing, but in the presence of this Hi. Okay? So, this Hi is now random, and you are asking yourself, okay, what is the effect of such randomness? So, it is very obvious that, so if you have a randomness or if you have some random variable, then I need to give you the distribution of this. So, let us suppose for the time being that it is Gaussian distributed and is of this form. Okay? I assume that all of you have done the first course in StatMech. So it is Gaussian distributed and of this form, and obviously when the strength of the impurities is very, very large, that is W is much greater than J, then what happens is very, very clear. The entire system just breaks into domains, right. So some of the domains are pointing up, some of the domains are pointing down, it just breaks, there is no global order, there is no phase transition. But you can ask a different question. What happens in the opposite limit? What happens when W is much less than J? So this was a problem that was of deep relevance to many people, and Imri and Ma came up with a very, very simple argument. So the simple argument is the following. Suppose you have so what does the random field do? What the random field tries to do is to try to align the field in the direction of the local, align the spins in the direction of the local field, random local field. So here is a cartoon of such a situation. So here, you know, the predominant spins are all pointing down, but there's a domain wall form, and within the domain wall are all up spins, for instance. Okay, and this is where the field is essentially switched from down to up, for instance. Now you ask the following question: does a uniform ordered state exist? Correct? Does a uniform ordered state exist? And of course, the answer to that question will be answered by what is the sort of competition, or whether the system can gain energy by going into a uniformly ordered state. Right? How will it gain energy? If you can go into a uniformly ordered state, essentially that means that that means that yeah. So yeah, how can it gain energy? So effectively, what happens is, if the system breaks into domains, then it's pretty obvious that the system has decided to gain energy by pointing in the direction of the random field, but it has to pay the cost of the domain wall, correct? So the domain formation always wins if the random field is less than the domain wall formation energy. So now how do you estimate each of these things? So if you look at the domain wall forming energy, the cost of the domain wall lives on the interface. If the interface is of size L, then obviously this energy is of the order of L to the d minus 1. What about this random field term? It's a random field term is again the sum of a large number of random variables lying within this domain. That should go as some L to the power d by 2 by central limit theorem. So you match both of these together and immediately you see that for all dimensions greater than 2, you can have a uniformly ordered state or homogeneously ordered state, whereas for d less than 2, it just the system would just like to pay the cost for the domain wall and gain energy by just pointing in the direction of the random field. But if it points in the direction of the random field at all points, then it essentially means that the system has broken up into regimes, where at some place the system is pointing up, at some places is pointing down. There is no long range order. So for all dimensions less than 2, the system has lost long range order by addition of infinitesimal amount of disorder. Okay, just a very tiny amount of disorder will kill the ordered phase. So that's the role. So now we'll show you something which is much more interesting. Okay. So we are now going to talk about a very simple system, and you know, sometimes your friends are very nasty to you, right? I mean, but then because they're so nasty to you, you also react, and sometimes very good things happen after that. So this is an example of that. So this work started out in 2018. What I'm going to present to you is a very simple example, of some very novel physics that comes out. And I have to say that we were not alone here. Actually, the group here with Jose and Professor Andrade, they had come up with a actually experimentally more appealing sort of model, which elucidates the same physics that I'm going to talk to you about. But I think my model is slightly more simple to explain. Okay. So what's the model? The model is a simple Ising model as such. Okay. But what's a new wrinkle to this model? The new wrinkle is I add a term which is antiferromagnetic, but that lives on the next nearest neighbor. So the nearest neighbors are all interacting with the ferromagnetic interaction, whereas the next nearest neighbors, which is on the diagonals, effectively are interacting with an antiferromagnetic. Very, very simple. The S's are classical objects taking values just plus minus 1. Very simple sort of physics. But this simple model actually contains a lot of very, very interesting information. So what is the very interesting information that we have on this model? So by the way, this is a very simple model, but it took all the way till 2013 for people to get the phase diagram of this model correct. Okay, it was done in this paper coming out of the Anders Sandvik group. So let's take some time to understand the phase diagram of this thing. On the x-axis is the ratio of the antiferromagnetic interaction to the ferromagnetic interaction. On the y-axis is T by J1. The phase diagram, obviously, when J1 is large and J2 small, that is somewhere over here, then you would expect the simple Ising physics to take place, right? That means you will have to have a magnetically ordered state, which is ferromagnetically ordered. So that's a ferromagnet. And then as you increase the temperature, you go into a paramagnetic phase. But very interesting thing happens when J2 by J1 becomes larger than 0.5. In that limit, what you get is this this set of what are called stripe ordered spaces. Okay? So effectively what happens is that either they can be arranged in a way that, for example, all the spins are aligned this way, and then this set of spins are antiferromagnetically aligned to that one. So it's like vertically ordered stripes, and its counterpart, which is the horizontally ordered stripe. Sorry, this is a vertically ordered, this is a horizontally ordered stripe. And each of these stripes in itself can flip entirely, right? And that's why you have a Z4 order. So this is a Z2 and this is a Z4. Now this transition is very much like the Ising transition people have studied. This was actually a very, very interesting transition, because from the point A to point B, it was first order transition, and then from B onwards is a line of continuously varying exponents. It's what is called, for the experts in the audience, the Ashkin-Taylor universality class. Okay? So we came in and we asked the following question: what happens to this phase diagram if you put in vacancies, impurities? Any idea? Okay, so let me kill the suspense there. So what we had thought, and when we started this work, what we had thought was that nothing very impressive will happen over here. You just put in impurities, and this first order transition will get rounded by a version of the Imri-Ma argument, and maybe this comes, the critical temperatures come down because disorder just tends to reduce the critical temperature, and you'll get some simple random mass physics. That's what we thought, okay? Because vacancies effectively is random mass. So this is the disordered Hamiltonian. So this rho i's can randomly take values 0 or 1. That's where the disorder is hidden, okay? So my student started doing the Monte Carlo simulations for this. So here is the order parameter, which is like the stripe order parameter, which is the equivalent of the magnetization. And look at how the magnetization or the stripe magnetization actually behaves. As you increase the system size, the magnetization actually starts going down. Okay? That's strange. And it's obvious that as I keep increasing, if I could do it, right? If I could do it on a computer, this magnetization will just go down to 0. So the order parameter goes down to 0. That was weird, extremely weird. Look at this, the susceptibility. You remember the susceptibility has to diverge, but now we are in a finite size system, so that divergence is cut off because of the finite size, and that's the peaks over here. But what is interesting is, as you go into larger and larger system sizes, it starts developing a secondary peak at 0, close to 0. And we don't know what's happening there. So we did some more stuff. We did real space maps. We did real space maps on the Monte Carlo samples that we have generated. So this is something called the nematic order parameter, and the nematic order parameter just tells you whether it's horizontally ordered stripes or vertically ordered stripes. That's it. What you see is that the entire system breaks up into domains. It just breaks up into domains. At this point, it's very clear, but at that point I didn't know it. This was just random field physics coming into play. That is, a system which had vacancies in it, which we thought to be just purely random mass, somehow is generating a random, in an emergent fashion, let's put it this way, in an emergent fashion, because it's a fashionable word to say, in an emergent fashion, it's actually breaking up into domains. Okay? Very much random field physics. What's happening? So to understand that, what you need to do is to go back to the basic physics. So what you're doing is you're removing vacancies at random. When you're removing vacancies at random, what happens is there will be situations where there are two vacancies that are sitting either next to each other on nearest neighbor bonds. Now they can sit on nearest neighbor bonds horizontally or vertically. When they sit horizontally, a simple back of the envelope energetic calculation at 0 temperature tells you that it picks out if the two vacancies are sitting horizontally, it picks out the horizontal stripe. If it's sitting vertically, it picks out the vertical stripe. So that's like having a field there, right? That's like having a random field, and the culprit that generates this random field is the presence of these two vacancies that sit side by side near on the nearest neighbor sites. So if you have two vacancies that are sitting across a horizontal bond, it picks the horizontal stripe. If they are sitting on the vertical bond, it picks the vertical stripe. That's random field physics. So effectively what it does is the Z4 symmetry of the problem is essentially being broken into some Z2 cross Z2 by the presence of this field. We can actually estimate how that goes also, right? So the Z4 is essentially broken to Z2 by Z2 by the emergence of a local random field. And this local random field effectively maps some model back onto the random field problem that we have been studying some time ago. And that's why you get these breakup of domains. In fact, we have actually, so this is for a concentration of quarter of the sites are removed, but you can show that this argument goes through for infinitesimal disorder, right? This argument goes through for infinitesimal disorder, right? So, that means that these stripe phases just melt away. And this is actually very important because such stripe phases are actually seen in many strongly correlated systems, like for example, high TC superconductors, there's iron-based superconductors and so on and so forth. So the question that we have to now ask is there any way that we can get back the physics? Or whether get back the stripe phase, whether we can get back the stripe phase. So one of the ways of doing it is we came up with is to put anti-correlations in the disorder distribution. So see to it that we prohibit nearest neighbors to having vacancies, okay? So no two nearest neighbors can have two vacancies sitting on it, either horizontally or vertically. We did that and voila, what do you see? You see that the magnetization, which in the case of uncorrelated disorder, where allow vacancies to sit anywhere, that essentially goes away and you get a magnetization which is actually as well behaved as you would want to. The secondary peak just washes out and you get exactly the sort of critical behavior that you would have wanted. So putting things together, what you see is that the presence of anti-correlated disorder essentially sees to it that you get back the stripe phase. Okay, so the stripe phase comes back on if you put anti-correlated disorder. We have gone ahead and figured out what the critical behavior across all these lines are. They all are disorderizing. It took some time to figure it out, but that's what it is. There's another way of bringing back the stripe phase, and the other way of bringing back the stripe phase is by putting the system on strain. That means what you do is you either stretch or squeeze the sample. If you stretch or squeeze the sample, the way we have modeled it is we change the vertical and the horizontal bonds, the nearest neighbor vertical or horizontal bonds, by an amount delta J. That's how we incorporated strain. Once you do that, for example, in this case, it picks out the vertical stripes. Once it picks out the vertical stripes, okay, so we don't have time to go into it, what happens is that the model gets mapped on to a random field Ising model in the presence of on top of a constant field, okay? This itself maps on to some sort of a percolation problem, and what happens is that for very small delta J, you essentially see a spanning cluster percolate through the sample, and then there is a spontaneous breaking of the remaining Z2 symmetry, which is what this shows you, okay? So that was too quick, I know, but I have some more. How much time do I have? 5 to 10 minutes? Okay. Fine. All right. So now I tell you something which is quite new, and this is about the effects of disorder in a certain class of transition called quantum phase transitions. So this is a very simple sort of model. So here what you see over here is the resistance at different temperatures in a heterostructure made of these two materials, and the resistance as a function of temperature, as a function of magnetic field at different temperatures. So what you see is there is a crossing from a low resistance state to a high resistance state. The low resistance state is essentially a superconducting state. You can show it is a superconducting state. The high resistance state we will not talk about right now, but it could be a metal, right? So the question is, how do you understand the behavior of such transitions? So these transitions are actually very, very special, because the reality is that you want to look at this transition exactly at t equal to 0. Such transitions are what are called as quantum phase transition. So how do you study such phase transitions? So such phase transitions are studied by effective field theories. These effective field theories can be derived from microscopic model. From the microscopic model by doing what is called Hubbard-Stratonovich, integrating out the fermions. So that's not important for you right now. This has been done from the 70s by Hertz, and Millis in 93, and Belitz and Kirkpatrick, who got the same theory for an itinerant antiferromagnet. Don't worry about all of that for the time being. The more important thing is the phi is a superconducting order parameter. This mod omega is essentially the damping that is felt by the superconducting order parameter because of the presence of the underlying fermions. Okay? You map this mod omega into real time. This is a long range 1 over tau minus tau prime square sort of interaction time. Delta naught is your tuning parameter, just like R or T was, which is T minus Tc by Tc. Here you go through the transition not by tuning a thermal quantity, but a non-thermal object, which like a magnetic field. Okay? So this, where all the curves are crossing, that's where essentially the critical point lies. Okay? That's BC. We'll come to this inset in a minute. So such systems were studied in quite a bit of detail. One can do the standard Wilsonian RG that I've been talking to you about, but they are not good enough. Okay, they lead to what are called runaway flows, and you cannot make any sort of experimentally relevant predictions for this. So to understand this, to understand the effect of impurities, we should realize that the distance to criticality now, because of the presence of disorder, becomes function that depends on its spatial coordinates. So for a long time, people were trying to analyze this problem, but it took these guys in 2007 and 2009 to come in and to tell us how this is done, and how this is done for an effective field theory of this sort. Okay? The way they did it is by going into some sort of a large N theory. That's not important. What is more important is that the effective theory we started out can be written in a very simple manner in this way. So what they have done is they have written a discretized theory where you have, think of Josephson junctions sitting on a lattice. Okay? This Josephson junction essentially has some sort of an order parameter which is given by this phi I, and they are talking to each other via this Ji. Okay? But on each of this there is a distance, on each of the Josephson junctions there is a distance to criticality. This omega, mod omega, essentially is related to the damping that each of these Josephson junctions feel. And this kind of what really happens in a real material. The real material breaks up into like domains, and these domains are talking to each other via this Josephson coupling J. This is exactly the sort of thing that these guys came up, starting from the phi-4 theory that I just wrote down. So what Jose and Thomas and Chetan did was to come up with a theory, but a renormalization group, not in terms of integrating out in real space, but really playing in terms of energetics. So what they said is that if this J is the predominant object, then the rotors on different sides, or the Josephson junctions on different sides, would like to have their phases in the same direction. Okay? So an ordered phase would win there. If the epsilons, which are the local gaps, are the largest scale, then essentially the disordered phase would win. And a critical point obtains when log J is equal to log epsilon. Don't worry about where the log comes, that's because of a certain reason, okay, which we don't go into right now. So people had done this for all sorts of values of the dynamical exponent z. We will not get into it, But what was very interesting is that they found a very interesting new physics, and the very interesting new physics was that they found a new class of fixed points. And the new class of fixed points essentially had the same critical behavior as predicted by Daniel Fisher for a class of magnetic systems called random transverse field Ising models. Okay? So this was the first work, I mean almost the first work which gave us a very clean physical description of what such transition should be, at least to my knowledge. So these results of RG can be extended to look at the phases, and in the phase what you see is off criticality, the correlation time essentially diverges as a correlation length raised to some exponent which is non-universal. Look at this delta naught. This delta naught was B minus BC, right? So depending on where you are in your phase diagram, this non-universal exponent would be different. So that's the smoking gun for most of these experiments, whether you can come up with a non-universal exponent z which changes throughout the phase diagram and diverges exactly at BC. So how much time do you have? Okay. Okay, so let me quickly go through this. So what we did with this data, which I'm part of the collaboration, was that we took the resistance and we tried, just like the magnetization you saw earlier on, we tried to collapse this resistance curves by using a scaling form of this form. In effect, what we are trying to do is to figure out what is the exponent combination nu z. In the previous slide, I just told you that if it's all conventional physics, then the dynamical exponent z should be some number. Whereas if there is this disorder-driven physics that Jose and Thomas and Chetan have found out, then it should be something which is non-universal and varies according to how far you are away from the critical point. Okay, so we tried to figure that out by using the scaling form. Okay, so in general, what we are trying to show is to show that this nu z is essentially a t dependence, or this nu z is an effective nu z which is a t dependent nu z, and we are going to calculate what that is. Okay, so to do this, what we have done is we managed to extract the z nu by doing data collapses for a set of curves which are close together. Okay, for a set of temperature curves that are close together, which is on the left hand side, we actually managed to figure out what the BC is and at what the BC is, and from that we essentially figured out how to do a data collapse. The data collapse gave us a z nu, and this z nu we could essentially plot as a function of B minus BC. What you find is extremely interestingly that as you come close to come close to an object called BC star, this z nu actually diverges. Okay, this z nu diverges, and it diverges exactly as predicted by Jose and Thomas's theory. So everything looks good. So I don't have too much time, but I'll tell you, all of this looks absolutely amazing, except that there is a kink. So for temperatures that are greater than 0.07 Kelvin, you essentially see a divergence which follows exactly the predictions laid out by Jose and Thomas. But what happens is, if I decide to write the nu z as an effective nu z, then the presence of a quantum critical point tells you exactly how that relation should be. And that relation should be that 1 over nu z should go as a logarithm, or 1 over logarithm. But what happens is, when I come lower in temperature, the nu z combination, or effective nu z combination, deviates away from the logarithm as predicted by Jose's theory and becomes a power law. This power law divergence is incompatible with having a quantum critical point. Okay, so above 0.07 Kelvin, everything looks exactly as predicted by the theory. You get what is called the Griffiths phase, which is where the dynamic exponent keeps on changing as you come close to critical point and so on and so forth. But once you go below that, something is killing the Griffiths phase. And what is it that is killing the Griffiths phase is an open question. We have an idea for this, but that will take a bit more time. This ramification essentially can also be seen by using an activated scaling ansatz for your resistance. And you see that up to 0.07 Kelvin, the curves map onto it exactly like your magnetization data that I started out with, maps beautifully onto these two curves. But below that, the scaling collapse just doesn't work. What does that mean? That means that there is some other physics that is going on in there that is killing off the transition, or killing off the quantum transition that was predicted by Jose, Thomas, and others, right? And what that is something which we can, I think, I'm out of time? Okay, so so very quickly, so we have an idea of what that is, and what that is something called smearing of a transition. And this is caused by essentially the physics that Jose and Thomas and have elucidated, along with long-range interaction, random long-range interaction. These things to come together conspire to destroy the transition. Okay, so this destruction of the transition. So there's more stuff. Okay, this destruction of the transition is actually seen by the existence of the low temperature tails in the phase diagram. So what have I? So in this talk, what have we said? Okay. So we have said that, look, disorder can do lots of very, very interesting things to a phase transition. The simplest thing that can do is just alter the universality class. But we have also seen that very simple sort of disorder can destroy phase transitions, can completely smear phase transitions out, even in very classical sort of systems. What we have seen is that there are much more interesting disorder effects when you go to what are called quantum phase transitions. In these quantum phase transitions, disorder can generate what are called Griffiths phases, and these Griffiths phases are seen, for example, in the superconducting transition. We also saw that the interplay between Griffiths phase and long-range interactions, they could actually destroy the transition itself. A real a real renormalization group picture of such destruction is still not available, at least for the superconducting system. There are some hand-waving sort of arguments, but that's just that. Okay, so that's a list of things. So in this talk, what I have not talked about is some other disorder stuff that I've been working on. So this is a list of this, and there's a huge list of to-do problems with Jose, which is why I visit him anyway. So thank you for your attention, and I know I maybe went over the talk a bit. Thanks a lot for your attention.
Thank you very much, Raj. Do we have any questions from the audience? I have one over there. Yeah.
You can shout, it's okay. You want this mic?
Hi, thanks for the presentation. I just wanted to ask, how does the experiments are conducted? Because on the stripe phase, when you induce disorder, how do you maintain the system stable enough for you to collect the data to study? How does the experiments get?
The experiments that I showed you were numerical experiments. So these are Monte Carlo data, right?
Oh, okay.
But the physics is actually okay, so in a real sample, this is exactly what you're going to see. Now, what happens in real systems is that the real systems are actually a finite size, correct? What could happen is the disorder concentration is so small that the domains, these domains are larger than your system size, and you will see it. So in real experiments, you might still see a stripe phase in a finite sample, but that stripe phase is not the thermodynamic limit. I mean, it will melt if you could make the sample larger. So these things that I just showed you was numerical data. I think the theory that Jose and Matthias Boita and Rade has developed, there are real material and that's exactly the same thing where you get these emergent random fields. There are, I think, real pyrochlore materials which actually show the melting of this order. So that's actually there. That's right, Jose?
Thank you.
Any other question?
I actually have a question. On your model in 2018, you showed that the magnetization falls with the size of your with your region, and you said that was quite surprising. I didn't quite understand the reason for that, and I was wondering if it's related to this thing of correlation length or border effects on your.
So that is where the random field gets generated, and once you have a random field, then no matter how small the impurity concentration, it will always melt the order. So what we thought is just putting in vacancies would just mean that you reduce the critical temperature and nothing more. But what it does is it generates this random field, and the random field just breaks the system into domains, and that is what you see when the magnetization keeps coming down. So as you go to larger and larger system sizes, you will get these. You will see these more and more of these domains. That's what it is.
Okay. Any other questions from the audience? I guess not. So if we don't have any more questions, I would like to thank Professor Rajesh Narayanan again. Thanks. Colloquium is closed.